Welcome to our discussion on minerals. Minerals are considering the building blocks of rocks. And in this chapter today, or this discussion today, we're going to at least devote 17 slides or so in this discussion to basic chemistry principles, because I believe to really get an understanding of what a natural substance from nature like a mineral represents, one must have some type of understanding of basic chemical principles or basic chemistry. And so if you've had a year of high school chemistry, that would be really great, because this would be a fantastic review for you. And in fact, you should recognize most of the basic chemistry principles that we talk about. If you have not ever had a chemistry class, which there are a few students taking this class that's never had a chemistry class, don't worry. We can get you through this, because I, again, present just the very, very basics of chemistry, and there's no math involved, just the concept of compounds and atoms and how they combine with one another and so forth to form minerals. And so I believe that then that would be like the first 17 slides. And then the next remaining slides then will be devoted just to minerals. And we'll look at some of the properties of minerals and how atoms come together to form particular types of minerals and so forth. This particular discussion, we start maybe with using the smallest known particle, which will be the atom in this case. And then we're going to build on these atoms using the basics of chemistry. And we'll build on these atoms to produce compounds or chemical compounds, which basically is the same thing as a mineral. And so for the lab exercises, folks in the lab then this week will also be looking at actual minerals. Again, this will be through online. You'll be looking at minerals online. And you will be learning how to identify minerals using the mineral's physical properties, which is very dependent on the mineral's chemical composition. And so that's kind of where we're headed with this discussion. We'll look at chemistry first, and then we'll take that chemistry and we'll apply it to minerals. So what makes minerals and what makes rocks? Well, to begin with, we're going to start with elements. And we'll talk a little bit more about what an element represents and what makes up an element and so forth. But for the most part, there will be at least, I'm thinking probably 8 to 10 elemental symbols that you will have to certainly commit to memory. And so as we go through this discussion, we'll certainly point these elemental symbols out. In fact, if you look at the slide here and you look at right under elements, we have iron, which is Fe, Mg is magnesium, then Si is silica, O is oxygen, and the K is the element potassium. And so elements then, and here's some pure substances that represent elements. So here's silica, what would look like under its pure substance, and here's oxygen, and then here's some pure, what we call elemental iron. And so together, when we combine elements together, elements make minerals. And in this case, we can call this a chemical compound. And so some of the common minerals that you'll see both in lab and that we'll look at here in this discussion is quartz. And believe it or not, quartz is the combination of both silica and oxygen. So what's interesting about chemistry, just to kind of begin with, you'll take silica and oxygen, which are completely different substances in their elemental state, combine them together, and now you make a completely brand new substance that we call quartz, which is actually the most common mineral on the Earth's surface. Another example of a mineral would be orthoclase, and the orthoclase involves silica, oxygen, and this time nature has put a little K in there, or potassium in this case, and that really colors the orthoclase kind of its pinkish color. And then we have another common mineral, biotite. And biotite is a typical combination of iron, magnesium, with, again, some silica and oxygen. And we're going to find out that there's more than 3 minerals. I mean, there's going to be 4,000 plus minerals. But the point here is to show you that elements combined together make minerals. And if we combine minerals together, then we can make rocks. And most of you who've had some type of earth science or geology courses in the past are probably familiar with the three major rock groups. And IG is just an abbreviation for igneous rocks, and then sedimentary rocks and metamorphic rocks. And so those are the three major rock groups. Here's an example of igneous rocks, and probably the most common continental rock on Earth is granite, which is a igneous rock. Then sandstone, which is a very common sedimentary rock, sandstone. And then this one here pronounced as gneiss. And this is a very common metamorphic rock. So again, in this discussion, we're going to focus more on elements, the basics of chemistry, and we're going to make minerals. And then the next discussion, we're going to devote that entire discussion just to rocks. So that's kind of where we're headed with the minerals discussion. So we need to now take a look then at the most basic, smallest particle. And so again, for folks who've had chemistry, this should be a pretty good review for you. But we start with the most basic atom model. And the key word here is model, because nobody has really seen what an atom looks like, except maybe for the last 10 years. I actually got some pictures of some real atoms that I'll show you. But when we say model, it really describes the behavior of material. And then that really outlines what chemistry means. Chemistry really is a science that describes the behavior of material. And the way that behavior is described is using models. And so back in the 1930s, I believe his name was Bohr, he developed a model of an atom based on how material behaves. And so this model of the atom then shows us some components. And if we look at what we call the subatomic particles, which are the particles that are inside of the atom, we can start with these little plus charged type subatomic particles. And these are known as protons, and the protons are located within the nucleus, and the nucleus just represents inside of the atom. So we have protons, which are positively charged particles. Then we have neutrons, which are also situated within the nucleus, and these are neutrally charged particles, and we'll get to what their significance is in a little bit. And then surrounding the nucleus, we have negatively electrically charged subatomic particles, and these are known as electrons. And so a couple terms that are very important with respect to describing the nature of this atom are very important, and these are terms that even if you have not had a chemistry class, you need to commit the meaning of these terms. And if you've had a chemistry class, this should be review. But our first term is the atomic number. And the atomic number represents the number of protons that are found within a typical atom. And we're going to find that every single element or atom has a distinctive number of protons. There are no repeating proton numbers for any element. And because of that, then again, we're describing the behavior of materials. Because of that, the individual number of protons, or the atomic number, determines the chemical characteristics of each one of the elements or atoms. So when we say an iron atom versus a silica atom, they will have differing numbers of atomic numbers or differing numbers of protons, which is, again, describes that particular types of physical properties for that particular atom. And typically we'll look at the periodic table here in a little bit, and the atomic numbers typically will range from number 1, meaning 1 proton in the nucleus, that would be the atom hydrogen, to 92 protons in the nucleus, and that would be UR's, the uranium atom. So we have protons, neutrons, and electrons. Now, the atomic mass is the weight of the atom, and the weight of the atom is determined by looking at the number of protons plus the number of neutrons. So we would say the atomic mass is protons plus neutrons. And really what the neutrons do is they are electrically neutral, and they basically will add weight or atomic weight to the atom. So although the protons will always remain the same number, the same element or atom can have differing numbers of neutrons. An example would be the difference between what we call a carbon-14 atom versus a carbon-12 atom. They both have the same amount of protons, which I believe is 6, but the number of neutrons will differ. And when we have differing number of neutrons inside the nucleus, along with the same number of protons, we refer to those as isotopes. And later on, when we get into geologic dating, we'll talk about the role that neutrons have with regards to determining how one atom will decay and lose neutrons and make another atom. But for right now, we're just going to worry about this term called atomic mass, in which we have protons plus neutrons. So again, let's do a quick, brief review of these two terms because they're very important. Number one term, atomic number, just represents the number of protons found in the nucleus. Atomic mass represents protons plus neutrons. So in the next couple slides, we're going to play a little simple math game, and we're going to determine how many neutrons an atom has, how many protons the atom has, and so forth. But before we do that, we need to talk a little bit about the electrical charges between protons and electrons. And you notice that protons are positively charged, electrons are negatively charged. And what's it mean when you have opposite electrical forces? Well, the opposites attract. And because of that attraction between the positive and negative charges of protons and electrons, you set up a situation in which the materials, the subatomic materials that compose the atom, basically stick together. And I like to refer to this as electrical glue. And so when you look at the behavior of material, or you look at all material on the universe, especially in its solid phase, it really doesn't want to come apart. And that is because it's being held together by the attraction between the protons and the electrons and the electrical glue. Now, one of the terms that we need to talk about to illustrate that electrical attraction is, let's count the amount of protons inside this particular atom. If you count them, you'll say, wow, there are 6 protons in the nucleus. We would say then that this particular atom has an atomic number of 6 protons. They're all positively charged. Now, count the number of electrons that you see on your slide. And if you count the number of electrons, it also has 6. So we have 6 positively charged protons, 6 electrically charged electrons. And what we say then is that this particular atom is electrically balanced or electrically neutral. The positives are the same as the negatives. And given that combination and that situation, that allows this particular atom to have a whole host of predictable and various type physical properties. In fact, this is really an element. All elements are what we call electrically balanced or electrically neutral. So if we say that we have an electrically balanced atom, and we say that the atomic number is, I'm just going to give an example, is 10, then that being electrically balanced, that means that there's also 10 electrons. Okay, so just to kind of reiterate, an electrically balanced atom is where the number of protons, or the atomic number, is equal to the same amount of electrons. At this point, we don't care about the neutrons. They're just adding weight, and that we'll look at those again at a later date when we get to geologic time. So, given that information, let's see then if we can now play around with adding and subtracting and using the concept of atomic number and atomic mass and answer these questions. So this first question you see on the screen says if an electrically neutral atom has 53 electrons, how many neutrons does the atom contain with an atomic mass of 96? So you get to use a little algebra where you add both sides and subtract both sides. But I also think if you understand the meaning behind atomic number, atomic mass, and you understand what an electrically balanced atom represents, then I believe you can do these in your head. So if we look at this again, we say if an electrically neutral atom has 53 electrons, right there, we should now know how many protons that this particular electrically neutral atom has. Because we know that if it's got 53 electrons, then it must have 53 protons. And if we know it has 53 protons, and we're looking for atomic mass, which is protons plus neutrons, then we know that the total mass is 96. We should be able to say 96 minus 53, and that should give us our answer for the amount of neutrons. So kind of repeating a little bit here and looking at the text on your slide, electrically neutral means electrons and protons are balanced. So we have 53 electrons and 53 protons, which means atomic number is 53, atomic mass is 96. So if we're going to calculate the number of neutrons in this particular atom, we would say 96, which is the atomic mass, minus 53, which gives us a total of 43 neutrons. So your job is to practice this. Your job is to hammer down, again, the meaning of atomic mass and atomic number and be able to manipulate those values along with understanding the neutral balance and come up with the different types of answers. This next one I'll let you do, and this one says if an electrically neutral atom has 24 electrons, how many neutrons does the atom contain with an atomic mass of 42? All right, and I'm going to pause for 1 minute and let you figure this out, and then we'll continue. Actually, let's go for 30 seconds. So hopefully you said, okay, if an electrically neutral atom has 24 electrons, then it has to have an atomic number of 24 because it's electrically balanced, and therefore the atomic mass is 42. So we would say 42 minus 24, and 42 minus 24 would be 18. And so your answer in this case would be B, 18, which means we're looking for 18 neutrons. All right, if you noticed, this particular question was exactly the same as the example that we just looked at previously, except in this case, I just changed the numbers. So let's up the ante a little bit and kind of test your comprehension on atomic number and atomic mass, and take a look at this next question. If an electrically neutral atom has 32 protons, what is the atomic mass number if there are 10 neutrons? How many electrons is contained in this atom? So the yellow number in the answers below are the atomic mass, and the gold answers below are the electrons. See if you can find the correct combination. I'll give you 30 seconds. Okay, that looks like about 30 seconds. So the way that I'm looking at this, electrically neutral, that means there are 32 electrons on this thing, which means that it's either going to be A or C. And we're looking for the atomic mass, which is protons plus neutrons. That's 32 plus 10. That becomes the atomic mass, which is 42. So I believe the answer in this case is A. 42 is the atomic mass, and 32 would be the number of electrons. So again, as we did in the previous question, you need to learn prior to exam time how to manipulate the numbers between atomic mass and atomic number, and understand what an electrically neutral atom represents. Now, I understand there are some YouTube videos that explain what we've kind of gone over in the last couple slides. They are much more entertaining than this lecture. There's a lot of cartoon type explanations. So I would encourage you then to, if you are not quite there and understanding how this works, to certainly observe and see some of those YouTube videos and see if you can hammer down the concept. And you should be able to, by exam time, do this in your head. Okay, the next slide now shows you some actual pictures of atoms. And it really wasn't until probably maybe 10 years ago that technology has become sophisticated enough to be able to look at atoms. And in this case, we're looking at atoms that are very, very, very big atoms, because the higher the atomic number of the atom, the larger the atom becomes. So in the first slide, or the first picture up here in this slide, represents the element germanium. And these are germanium atoms, which I'm also assuming that there's some other atoms in there. And so there's a couple observations to take home with this. And I noticed when I first looked at atoms, I was just in awe and in wow. Because first of all, if you look at them, each one of the atoms kind of take on that spherical shape that was really proposed by Bohr back in the 1930s, based on his experiments explaining the behavior of material. Because remember, he came up with the model of the atom. And the other thing I noticed, which is just amazing and awesome to me, especially as a scientist, that even at the molecular level of material, there is a pattern or a design in terms of how the atoms are put together. And we're later going to take this concept and we're going to look at why minerals look the way they do, because there is definitely an ordered pattern of atoms that are all bonded and connected together. And again, when I saw this geometrical arrangement of real life atoms and the design behind each one of the atoms, again, I was just in awe. It was very amazing. I also believe that to enhance the picture, the atoms were colored. And so I think that the colors are just the enhancement. So over to your right here on your screen, you see cobalt atoms bonding with copper atoms. And again, you see that same internal geometrical arrangement of atoms. You see a nice design of patterns, even right down to the molecular level. This drawing now that you see below your screen, so this is not an actual picture of an atom, but this is a very important compound or molecule that we'll be looking at a little bit later in the lecture. And this is known as what we call the silicate tetrahedron. And the silicate tetrahedron basically is where we have one silica atom in the middle, and it is surrounded by 4 oxygen atoms. And we're going to find out in mineralogy, or in terms of minerals, that this is really what we look at as the basic building block of the largest class of minerals on the Earth's surface, called the silicate minerals. And so we're going to be looking at this silicate tetrahedra a lot more in depth towards the end of the discussion. So let's kind of shift gears and let's jump up now to take a look at elements and how elements relate to the periodic table. So in other words, PT here means a periodic table. And so if we look at elements, Most folks in their high school science classes or high school chemistry classes have learned that an element is considered a pure substance. And so we're going to kind of develop that a little bit and look at why it's called a pure substance. But again, all elements on the periodic table are considered pure substance. And as we mentioned earlier, each element has its own atomic number. There is no repeating atomic numbers for any other elements. There's no repeating, no two different elements with the same atomic number. And again, we'll discuss that a little bit later. There's about 118 known stable elements, or I'm sorry, 118 known elements. 92 are natural, very stable. And then we look at what we call synthetic elements, in which even scientists can make, but they're not very stable. They don't really last long under room conditions. So elements possess what we call distinctive physical properties. And when we say distinctive physical properties, we're saying that elements have a particular or a distinctive hardness associated with them. Elements have what we call a predictable boiling point. For example, if we look at iron as an element, its predictable melting point is just about 1,000 degrees. In fact, there's an exact temperature in which one can predict that when that reaches that particular temperature, the element iron in its solid phase can be predicted to move into its liquid phase. So predicted boiling points, every element can either exist as a solid, it can exist as a liquid, or a gas. So theoretically, you can certainly have gold, which is an element, can exist as a solid. I think we all can buy into that. But then given a particular temperature, certainly gold can be melted and exist as a liquid. And believe it or not, at a predictable temperature, gold can also exist at a vapor phase. Imagine that, walking into a room with gold vapor. Can you imagine what would happen if you inhaled gold vapor? Your lungs would instantly turn into solid gold. What a thought. Here are some examples of some elements that are in their pure state or pure substance, meaning that each one of these elements have their own atomic number that's given its pure state. And each one of these elements that I'm showing you at the bottom of your screen also are very electrically neutral or electrically balanced. And so we have Na, which is sodium. And so sodium is a natural common element. And again, as I go through these elemental symbols, you need to make sure you commit these symbols to your memory. So Na is sodium, Cl is chlorine, and Au, that would be gold. So here it is, the periodic table of elements. And a lot of students, when they first see this periodic table, they get scared and they start shaking in their boots. But really, we're going to I'll just look at the basic properties of the periodic table, and then later on relate the periodic table to how minerals form. So to start with, in terms of the periodic table, if you look at the number in the square of each one of the elements, so for example, where my arrow is, this is hydrogen. It says that the atomic number is 1, meaning it has 1 proton in its nucleus. And typically when we look at a periodic table, the number of protons or the atomic number will increase from your left to your right. So you should be able to take a gander at this periodic table and see that the atomic numbers are increasing. And as we mentioned before, there is no element on here with duplicate atomic numbers. Now, I don't know how many out there in online instructing world are going to be secondary teachers, for example, teach in high school, and even junior high. But if you want to buy yourself a good 15 minutes of silence with the students, and trust me, if you ever get into that situation, you'll want that 15 minutes. And if you ever want 15 minutes, you show the students, if you're doing a lesson in basic chemistry, you show the students a periodic table and you say there is one element on this table that repeats itself in terms of the atomic number. If you can find it, you get an A for the day. And you'll be amazed at about 15 minutes of silence, because those students will just pour over this periodic table looking for the repeated atomic number. And then eventually, after about 15 minutes, some student will raise their hand and say, I don't see any repeating atomic numbers. And then you say, yes, that is true. That's the lesson. And that really drives that home. Just a side note, I taught for 10 years at Delano High School, and I taught the sciences and earth sciences, and we would do a little exercise on the periodic table. And I would certainly do this every semester and bought myself some peace. Worked every time. So on the periodic table then, the periodic table is arranged by groups and by periods. And so when this periodic table was developed, I believe back in the 1500s, and I believe it was a scientist named Mendeleev, when he again started to organize these elements, it's exactly what it is. It's just a table that organizes elements. And Mendeleev just didn't throw a dart and say, gee, I'm going to put sodium here, I'm going to put silicon here, and so forth. Instead, the periodic table is organized by groups and which are similar properties. For example, you can have group 1 right here. So where my arrow is group 1. And all of these elements, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, are all organized based on similar properties. And that particular similar property in this case is that these elements are very, very, very reactive. And when we say reactive, if you take them out in the atmosphere, for example, or in the oxygenated atmosphere, they'll basically explode. And so we call these the alkali metals. So that should be a review term for folks who've had chemistry. So group 1 then, we will refer to on the periodic table as alkali metals. And then group 2, which where my arrow is, so this is group 1, this is group 2. Group 2, starting with beryllium, magnesium, calcium, strontium, barium, and radon, these particular elements are slightly less reactive than group 1. And these are the alkali earth metals. And so really what we're seeing here is if we start with group 1 and we work our way from left to right on the periodic table, we would say the reactivity gets less and less and less. So group 1 all the way to basically group 18, where my arrow is, in this red group of elements, and this is helium, neon, argon, krypton, xenon, and radon. Here, this is called the inert gases or the noble gases. And these gases don't react with anything. They just sit there and they're quiet. They do nothing. And there'll be some reasons for that with respect to the structure of the atom that we'll talk about a little bit later. So again, what we want to say is the reactivity of the periodic table becomes less as you move from to the left and to the right, becomes less reactive. So just a quick story. Let's go down to the sodium element, which is atomic number 11 in group 1, so it's an alkali metal. When I was working again at the Delano High School, next door to me, they hired a new chemist. And this new chemist was teaching some of our chemistry classes. And in the back room, we had a pure elemental substance of sodium. And we like to show it to the students as kind of a show and tell when we talk about the periodic table. But in order for this sodium to be stable, it has to be kept in oil. And so typically pure sodium is submersed in oil, so it doesn't have contact with any of the oxygen. Well, the story is that the new chemistry teacher, he went back in the back room and got the sodium, and he actually took the sodium out of the jar to show the students. And as he kind of took it out of the jar and presented it to the students, it didn't react with the air or the oxygen yet because it was still immersed in oil. And so he showed it to the students, and then apparently he took that sodium and tossed it in the trash can. And about 15, 20 minutes later, because our rooms were right next to each other, we heard a huge explosion, and it practically blew the trash can apart. And so we ended up having to evacuate the entire science building at Delano High School. We all had to go out in the parking lot, and the hazmat folks had to go in there and take care of business and so forth. Anyway, I was surprised. Well, really not surprised, but the next semester, I did not see that chemistry teacher. He was not asked to come back and teach. And I don't know, I would think a basic chemistry person would understand that sodium is highly, highly explosive because, again, it belongs to group 1 and it belongs to the alkali metals. So we can further take the periodic table. We can divide it into 3 distinctive groups. The first group, we can divide it into what we call metals. And metals, again, have distinctive properties associated with them. Later on, we'll look at these properties associated with metals as minerals. But metals, metals are easily bendable. They're good electrical conductors, good heat conductors. You can polish them. And so every element in this red box here have those similar properties. So we call those metals. And then, of course, the opposite of a metal would be over here on your right-hand side. We refer to these as non-metals. And if one can learn the properties of metals, then the opposite would be the properties of non-metals. So, for example, if a metal is very malleable, meaning easy to bend, then a non-metal is very brittle. Example would be you take copper wire bends pretty easily. You take a piece of glass, and what would happen if you try and bend glass? Well, glass would shatter, glass would crack, and that would have a non-metal type characteristic. Now, there also is a set of elements that display both non-metal properties and metal properties, and we call those metalloids. And so right here in this blue area of the periodic table represents the metalloids. So we have metals, metalloids, and nonmetals. Now, let me address real quick the term period. So we looked at groups in which the periodic table then is organized based on similar properties. And periods really have no relationship. Periods just are created by default when you make groups, right? You put groups together, and then you're going to produce periods. So interpreting the periodic table. So what I did here, because again, we're just looking at basic chemistry, typically in a periodic table, you're going to get 4 essential information, 4 essential components of information to the periodic table. Now, typically, if you look at other periodic tables, it could have other information in that little box describing the characteristics and properties of the element. But there will be at least 4 essential components. And so the first component, again, as we discussed earlier, would be the atomic number. And we know now that the atomic number represents the number of protons. That's typically in the upper part of the box, or maybe on the right or left side in the upper part of the box, but typically on the upper part of the box. Then you have what we call the elemental symbol. And in this case, I'm using the elemental symbol AU, which is for the symbol gold. Now, the first thing you should be thinking is, well, wait a minute, why not just make it GO? That would be reasonable for gold. But remember, back in the 1500s, when elements were being organized, this was in Europe, and the common language in Europe was Latin. So a lot of the elements are derived from Latin type names. And so I believe gold, AU, is pronounced azurus, and azurus meaning gold, AU. And so I'm thinking, well, wow, is there other elements that do the same thing? And I started thinking about the element iron, which is Fe. And the Latin term for iron is ferrous. Then I got really excited because I thought, okay, wow, I've driven on a Ferris wheel. And now you know where that term comes from. So a Ferris wheel really means a iron type wheel. Or how about the element lead? So for those folks who've had some chemistry, what is the symbol for lead? And that would be Pb. And the Latin term for lead is plumus. And when you spell plumber, you have Pb in the term plumber. And plumbers used to, not anymore, thankfully, used to use lead piping. And so again, a lot of our words today are derived from Latin, and certainly some of the elements as well. So usually at the bottom of the box, we look at atomic weight, which is protons plus neutrons. And then, of course, at the very bottom, it's going to typically give the elemental name. So in this case, we would say gold is an atomic number of 79. Elemental symbol is Au. Atomic weight is 197, and the element name is gold. And I just thought of something. If you know the atomic weight and you know the atomic number, how many neutrons does gold have? So I'll let you think about that and you come up with that answer on your own. So down here at the bottom of the screen, if you observe the periodic table patterns and the definition of an element, what characteristics distinguish one element from another? And so we've been kind of hammering this a little bit, and hopefully you're at a point now with some basic chemistry that really what really describes the elements or the characteristics is the atomic number. And so we would say in this case that the atomic number distinguishes one element from another element. And remember, I venture to say that if you really looked at an element, are you really going to find the number of protons? I don't know. All I know is that when we look at chemistry really looks at a man-made science that defines the behavior of material. And so gold has just been assigned 79 atoms or 79 protons. And those 79 protons gives gold those particular characteristics. Because again, it's a man-made science and it's describing the behavior of material. This next question down here at the bottom of your screen says, kind of goes back at the very beginning of when we started looking at elements. Pardon me. Start looking at elements, and it says, why is an element considered a pure substance? So this now answers that question that you had at the beginning of your high school chemistry class when they said, why is a element a pure substance? Well, think about this. Let's go back to gold. We'll take gold, which the atomic number is 79. And let's say that I walk in the class and I have a huge chunk of gold, 2 pounds of it. I probably wouldn't be walking in the class, but I have 2 pounds of gold. And what's the atomic number of that gold? And you would say, well, it's 79. Well, I'm going to be such a nice instructor that I'm going to take that gold and I'm going to cut it into small pieces and give everybody in the class a piece of that same gold. Then I'm going to ask you, what is the atomic number? And you'll say, well, it's still 79. Then we're going to actually take that gold and we're going to cut one little gold atom off of that little piece of gold that you have. And we're going to ask that question, what is the atomic number? And it's still 79. So the point is, a pure substance in chemistry can be defined by the consistent or the same atomic number. And so gold will always have 79, even right down to the very last atom. Eileen, something's wrong. I think I got to do it over. I don't know. Come here. I was able to pause it, but I wanted to stop it because this is my first part. Oh, it was a good lecture too.
Okay. So
and I went to pause it, and I don't see where it says done or anything. So I paused it, and it's still hanging out there.
Well, how do you usually end it?
I put I hit this escape, right? And then it comes up and it says done down there. Then I put done.
Why didn't you just end? I'm really confused. Why didn't you just end it now?
I did. I pushed escape, but this came up, not my normal done. Damn thing.
Well, it looks like it's there.
It's there, but I'm afraid to push any buttons. I'm end up erasing it. Oh, I have to do it again. It's a new twist on it or something.
It says slide 10. You did 10 slides?
Yeah, and I need to do this is part 1.
Okay, if I do resume.
Oh, if you do resume, you got to start talking on it again. It's gonna. Stupid thing.
And so you did what you always do.
I always push escape, right? And then it says, and then it comes over and it says done. Or did I push the wrong button? Maybe I pushed the wrong button.
I'm just going to minimize this. I'm not getting rid of it. That's your PowerPoint,
yeah,
right?
Well, you can get rid of that. I mean, I can come back to that.
Get rid of that?
Yeah. Oh.
No, here, hold on. Wait. It's here. I'm just deciding.